Good morning, everybody. I am Krishna Kumar. Thank you for the nice introduction by Divya and Vijumon. Well, it's a great opportunity for me to talk to you. This is the first time I am on a webinar, and it's a very interesting experience, I should say. And after conclusion, I will say what it is all about. But I hope the setup that you have here, that is the classroom, is visible to you. This is named Krishna's classroom for the purpose of recording lectures, and the channel named Krishna's classroom streams these lectures, and I hope many of them would be of use to you. Well, that's a slight promotion. Forgive me for that. Okay, let me start and straight away get into the topic. Now, we are going to talk about real life, which is probably the ground on which you play analysis. So you are all familiar with it. And also, it's a very interesting thing, and therefore some of the features of this real line should be clear to you if you want to feel comfortable doing analysis of that. That's why I have come up with this lecture. Let me open with a question. How does plants grow? This is one question. Almost the same thing is, how does the time flow? These are two crucial questions I am asking. Now, all of you would have observed that plants grow under conducive conditions. And how do you know that they grow? Because you can see every day the height of the plant is increasing, or a few more leaves are added to it, and so on. Second question is, how does time flow? I will come to the second one later. But if I ask this question, the answer I want in one of these two forms. Does it grow discretely or continuously? So the options are given, and I am sure that all of you would spring up and tell me that they grow continuously. This is your gut feeling about the whole thing. After all, had it been growing discretely, what would happen? You'll see that at some instances it will be jumping or jerking or something like that. This doesn't happen. Feel that it grows out of in a smooth flow of growth that you have. Same thing about the time. You feel that the time flows very smoothly, not discretely. It's not that you are jumping from one second to the other. Maybe your watch records only in seconds. Okay. But let us ask or try to ask the following question. What is it? How do you know that it is flowing continuously? Now, there is no way in which you can substantiate this, that it flows continuously. Why? Because there is a limitation for you to measure time. I believe you can look into the net. The time can be measured precisely up to an error of 10 to the power minus 15 6 seconds. This is the current position. Maybe it has improved slightly because you know that every moment some new instruments or now some new system is invented to measure it more precisely. So this is absolutely essential in the case of investigating nature. Okay. That is the limitation. So you just do not know how you are not able to measure it, or you are not able to see at the moment the time span being more precise than 10 to the power minus 15 seconds. Therefore, for all such practical purposes, time grows discretely. Okay? But certainly that is not the case. Maybe a year later you will see some improvement on this particular number. See more and more precise data. If you have to come back to this world after 100 years, you are going to see much more precision is available in these kind of measurements, and much more knowledge is added accordingly. So what you do is it's a hypothesis that time flows continuously. There is no experimental evidence to substantiate it, but it's your feeling. Now the real line is essentially a manifestation of time flow. This is my point. Okay? That's why it is considered to be with no gaps. Okay? It's considered to be smooth. But let us see how mathematician conceives, or this was the question asked. How do you, because numbers were in use for a long time. And it was only in the 19th century and 20th century that some form of precise understanding of numbers were achieved. And so there was it was absolutely essential to do it more mathematically, because mathematicians have certain ways of doing things. First of all, there is certain logic which supports it, and it should be within that logical framework. And there's a culture about the whole thing, and this is visible in the construction of the real number system. So the theme of today's talk is how the real line is constructed. Okay, so we start with the system of natural numbers, or what you call just the numbers that you use for counting. Okay, so this is defined as the set of all numbers, which is designated by 1, 2, 3. It's easily said, then explain what it is. Let us see how we get this. Now, it was Peano who gave a set of axioms which gives this system. So we start with the Peano axioms. There are 5 of them which describe the system. And you know, axioms are not something to be disputed, nor you attempt to prove any axiom. Because axiom is, see, when you say these are the set of axioms that define something, or you would have heard that the group axioms are there, vector space axioms are there, then you know Peano's axioms defining what a natural number is. I mean, you say that if there is a system which agrees to these rules that you lay down, so rules of the game, then you call it the corresponding system. So here, any set which agrees to all these 5 axioms that you write down, this is what you call the set of natural numbers. So let us see what they are. So the first one is that 1 belongs to, it says 2 things. One, n is non-empty and there is at least one element in it, and it will be with a special status soon, and it is called 1, and 1 belongs to n. That is, there is something called the first element. So it will be clear. Now the second axiom is that for every x belonging to n, I designate an element of n by x. There exists a unique follower, unique natural number or element of n designated by x prime called the follower of all these things are important. Once x is there, there is a unique follower or a unique successor, something that succeeds it. Okay, for instance, if you have 3, then it has a unique successor, and that successor we usually call 4. So there is exactly one element which succeeds the given element. What it says that every element of n, then it's a set. See, there is a kind of successor rule, namely that there is an immediate successor for every element. There is only one such element, that's why I put here unique. Okay. The third axiom is 1 is not the successor of any element. Which can be written as 1 is not equal to x prime for any x belonging to. That means 1 is not the successor, not a successor. Every other element is a successor. Person 2 is a successor of 1, 3 is a successor of 2, and so on. Okay, so 1 is not a successor of any element. The next thing is, see, we said that if you take one element, then it has a unique successor. Okay, right? Now what we are going to say is that you are going to talk about the predecessor. Because if x prime is the successor of m, then x is called the predecessor of x prime. So there is a relation. So I say that if x prime equal to y prime, then this implies, that means there is a unique predecessor. So the existence of a unique predecessor, existence of a unique successor. Now a predecessor is not available for 1. So except for 1, element 1. 1 does not have any predecessor at all. Okay. Now finally the induction axiom. This is very important. What it says is this: let script M be a subset of then if there are two conditions, one belongs to a script M, 2, the second condition is that X belongs to script M implies X prime belongs to just understand this condition. M is a subset of M, 1 belongs to M, X belongs to M implies X prime is also in M. Then M is the whole of. That means if M is script M is a subset of N with these two properties, then M is the whole of N. See, loosely talking, it says this: 1 is there, therefore its successor is there, therefore its successor is there, that is 3 is there, therefore its successor is there, and so on. So, you know, all the successors are there. So, you can get, you will see that M contains all these elements. Therefore, M is equal to N. Now, this is the whole idea of it. So, these are the 5 axioms which describe what is called the natural system of natural numbers. Now, within these 5 axioms, you can build a very nice system with a lot of structures imposed on it. Now, this is what you are doing. I mean, see, all these are developed out of our day-to-day experience, as you can see. Now, we will go to addition. There are 3 structures on the system of numbers. One is addition, then there is this order, and three operations on it, which gives you certain structures on the system. Now let us take up one by one. Look at addition. Let me define this. Okay. How do you define addition? How did you define addition in your school days? You defined it as, or your teacher would have told you that it is the repeated addition of 1. If you are to add 3 to 5, then add 5 times 1 to 3, 1 by 1. By which you mean 3 you take, add 1, you get 4, then you add another 1, you get 5, then you add 1 again, you get 6, likewise 7 and 8. Now this is how you do it. Okay, so we have to capture that idea in our definition. See how beautifully these things are done in mathematics. So the definition is that we define x plus 1. This is the first time we are using this symbol. This is defined as x prime for any x Now the second condition is that x plus y prime equal to is defined as x plus y prime. Now this is a bit soft. This is very easy to understand. Now let us see whether this gives you the addition. Check with an example. This is the best way to understand it. Okay. Also, you want to add 2 to 3. Let us work this out. You want to add 2 plus 3. What is 3? 3 is equal to, now this is a question that you are asking. So note 3 is equal to 2 prime. Therefore 2 plus 3 equal to 2 plus 2 prime. Now you can apply this. If you apply this, this is going to be what? 2 plus 2 prime. What's the definition? Okay, but what is this? Again, you would note that 2 is 1 prime. Therefore, this is 2 plus 1 prime prime. But what is that? That's equal to 2 plus 1 prime prime. Am I right? Then the next one is, you have, what is 2 plus 1? 2 plus 1 is equal to 2 prime. Then you are taking the prime of that, you are taking the successor of that. So how do you get the number? You take 2, its successor is 3, each successor is 4, each successor is 5. So you get 2 plus 3. This is exactly what we learned in your schools. Okay? And this addition is described through repeated addition of 1. That's what you see here. So many primes come. Now, I'll just take out some of these things. Keep these piano saxons in your mind. We'll be using it left and right. In fact, see, the important thing in mathematics is when you do pure mathematics or rigorous mathematics, once you, or axiomatic mathematics, you always play within the rules of the game, namely the axioms. You are never allowed to violate this. If you are violating it, then you are playing a different game. It's like chess. Chess, you know that it has certain structure, like 64 squares, alternately white and black, and 2 sets of 32 pieces of to fight a war on the board. And then each entity has a specific movement. These are all the rules of the game. You are not supposed to violate them at any stage. Whether you are a novice or a grandmaster, use the same rules. But the game that you play may be quite different. Therefore, mathematics is exactly like that. So you have the axioms. You are not supposed to violate the axioms at any stage. Now, one of the things that you have to prove is that you have written down a definition, but before you call it a definition, you have to prove that such a thing makes sense on. So show such a thing makes sense on N. That needs some work, because you have to play within these rules and show that this is consistent. Whatever you have written here is consistent, or in other words, given 2 elements, you can always add. Okay?